Hello, this is Dr. Lori. Welcome to this second part of looking at standard deviation and standard error. So what we've noticed is that standard deviation really describes the variability for individuals, and standard error really describes the variability for means. So let's take a little bit of a closer look at what that can look like. If we were to then create a distribution based on standard deviation, we would create a normal curve like the one that you see here, and the location would be defined by the mean, and the spread, how far spread out it is in either direction, would be defined by the plus or minus 1.96 standard deviations. And then that middle section, all except for the little tiny bit that's in the tails, over here 2.5% at each side, this 95% here in the middle, would define 95% of the individual observations. So that mean plus or minus 1.96 standard deviations estimates the range for 95% of the individual observations. On the other hand, if we're thinking about standard error, then that mean plus or minus 1.96 standard errors really is an estimate of the range for 95% of the means of repeated samples. So if we took samples over and over and over again of the same sample size, then this 95% range right here, this 95% middle part, really is estimating the range for 95% of the means. So let's do an example, and we can actually calculate that confidence interval so you see exactly how that goes. Let's say that our x bar is equal to 150, and our standard deviation, so every 1, 2, or 1, 2 standard deviations is equal to 40. If I take repeated samples of size n equals 16, then my standard error, as we learned before, is equal to my standard deviation divided by the square root of n, which is equal to 40 divided by the square root of 16. Notice how very conveniently this is, you can take the square root of 16 without a calculator. So this ends up being 40 divided by 4, which is equal to 10. So my standard error then, each time I jump over, this is about 10 and this is about 10. So this ends up being 150 plus 10. Here's 160. Here's 170. Same thing in the minus direction. Here we have another 10 and another 10. So 150 minus 10 is 140 and 130. So this approximately 95% confidence interval of the mean goes anywhere from 130 up to 170. Now, the interesting thing about this confidence interval of the mean, it can tell you whether this mean is statistically significantly different from a fixed value. So, for example, let's say I was doing a one sample t-test and I had a null hypothesis that mu is equal to, let's just say 155. So here's my null hypothesis. The alternative hypothesis would be mu is not equal to 155. Now, if I were to draw 155 in here, it would actually be right about in here, halfway between 150 and 160. There's 155. And just looking at that, you can say, well, that doesn't look very far away. In fact, it falls well within inside of this 95% confidence interval of the means. So if my null hypothesis is that the mean is equal to 155, I would say, yep, that looks pretty reasonable. Fail to reject the null, and conclude that our mean is not statistically significantly different from 155. If, on the other hand, I had a different null hypothesis, a different alternative hypothesis, let's say my new null hypothesis is that the mean is equal to, say, 180. Well, that would be approximately somewhere here. And you can see that that is outside of this cutoff of plus or minus 1.96 standard errors. And so the alternative hypothesis would be that the mu is not equal to 180. Because this is outside of that confidence interval, I can say this null hypothesis does not seem reasonable. It seems like that would be very rare for that to happen. In fact, less than 5% of the time, just by chance alone, if the mean really was 150. So the thing to remember here is that my standard deviation is 40. That means if I started with 50 and went plus and minus 2 times the standard deviations, I'd be way out here somewhere, right? And way down there. As the sample size increases, my standard error goes down. The bigger and bigger and bigger. So if I had, instead of sample size of 16, I had a sample size of 100. If I took the square root of 100, that would be 10. So this would be 40 over 10. That would be 4. So you can see how even much narrower this would be. So I would have a little tiny population in here. It would be narrower and narrower. As my sample size goes up, my standard error goes down. What that also does is it not only makes the standard error go down, but because the standard error is smaller, it makes this 95% confidence interval of the means narrower as well. So the standard error is smaller. That makes the confidence interval also be narrower. So narrower confidence interval and smaller standard error go hand in hand. So let's also, so here's a definition of a confidence interval: range of values so defined that this is from Webster, we love Webster, that there is a specified probability that the value of a parameter lies within it. Therefore, if we have a narrow confidence interval, the true effect ends up lying within a small range of possible values. So the narrower the confidence interval, we have this small range of possible values. A wide confidence interval has a wide range of possible values. Even if the wide confidence interval is statistically significant, remember when we did our hypothesis testing, we can test whether something is statistically significant. The true effect lies within this wide range of values, and so we know that we're not specifically too sure about that particular value, the location of it. It could be anywhere within that 95% range. There's one additional thing that I want to talk about with this particular topic, and so far we've really always used the 95% confidence interval. That's not always the case. We could also have a 99% confidence interval for the mean. That would be the mean plus or minus 2.58 standard errors, 2.58. We could have a 90% confidence interval. That's the mean plus or minus 1.64 standard errors. So you can see that we can choose a different level of confidence. We don't always have to choose a 95%. And along with this then goes the concept of level of significance. If we have a 90%, well, let's go to 95%. If we have a 95% confidence interval, we have an alpha of 0.05. The level of significance then that goes with the 90% confidence interval is 0.10. Notice that the 90% here and the 10% here add up to 100%. If we have a 99% confidence interval, then that goes along with the level of significance of 0.01. And so this 1% plus the 99% adds up to 100%. Now, very rarely will we ever be working with these numbers. It's much more common to see the 95% confidence interval, the plus or minus approximately 2 standard errors. That's what most journals would use. So just know that those other things are options. You probably won't be tested on them, but just realizing that that is something that some journals or some specific areas of specialty might use. Thanks for joining me.